My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. Good evening to all here in Bangladesh and a very good morning to all those who are watching this program live from USA. Hope you are well and safe from corona pandemic. So we are trying to adjust with this new normal situation. I think you have already come to know that our Department of Physics, Pabna University of Science and Technology has started its online program to continue our academic program. And we have started our international physics webinar also, and we have successfully completed our 96th international physics webinar. Today it's our 97th. So today I would like to welcome you all to a joint session between the Pabna University of Science and Technology and the MIT Kavli Institute for Astrophysics and Space Research, MIT, Cambridge, in astrophysics. And we have with us here today Dr. Tansu Daylan, a postdoc research scholar, Kavli, a postdoctoral fellow, MIT Kavli Institute for Astrophysics and Space Research, MIT, Cambridge, USA, and he has already connected with us. So I'd like to welcome our speaker. So good evening and a good morning to your part. So welcome to our International Physics webinar and welcome to our university and Bangladesh through online. And I think it's maybe your first collaborating program with any Bangladeshi university and any webinar with any Bangladeshi teacher or any university. Is it okay? Is it your first program, or you have already did your any other program in other university?
Any other university before
with Bangladeshi university before this?
No.
Maybe this may be your first program. So thanks for accepting our invitation. So we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology. So it's your time. You can start your session.
Okay, thank you very much. Well, I guess first, thanks for the invitation, and I hope this should be a nice introduction to the science of exoplanets. And I will start slow, basically go through the basics first, and then build up to hopefully, by the end of the talk, I would like to give a complete picture of what exoplanet research is all about and why are we so excited about exoplanets. And I will conclude the talk with a specific example of a system that got excited us more recently. So thanks for the introduction. I'm Tansu Daylan, and I'm a Kavli postdoctoral fellow. And I mostly work on exoplanets, although I did do some work in the past about dark matter as well. So happy to answer any questions regarding either subject. Okay, so I would like to get started by just taking you a few centuries earlier, just not so early, almost like to the beginnings of astronomy, but rather just a few centuries earlier, where just before the Copernican revolution, people thought that that the Earth was at the center of the solar system and the whole universe per se. And by then, it was not so possible to imagine that there could be worlds like our Earth outside the solar system, simply because the notion or the cosmological model of of how planets revolve were all centered around the Earth, and that did not leave room for much imagination. However, once we accepted the fact that the sun is actually at the center of our solar system, and obviously our solar system is not the whole universe, that there are other stars and potentially other planets just like our own that orbit those different stars, many millions and billions of them, we then eventually came to appreciate that the universe can actually be teeming with planets. And this, I believe, is a very profound realization, enabled through some 30 to 40 years of extensive research, although that research also has some history prior to the first discovery of an exoplanet, which happened very early 1990s. However, this was a research program that was being targeted for many decades, even before that. And there were many claims of discovery of planets beyond our solar system. That's what we call an exoplanet. However, they eventually turned out to be not so, real. However, by early 1990s, we started to regularly discover exoplanets, first via the so-called Doppler method, which is the idea that essentially stars change color periodically as massive bodies orbit around them. However, today I will not be focusing on that detection method. I just would like to mention that in passing and just highlight the fact that historically that was the very first method of detecting exoplanets. However, after about 10 years, in the very beginning of the new millennia, a new discovery method kicked in, the so-called transit method. And that discovery essentially opened up a much more efficient way of finding many more exoplanets. I will not go much into detail, but when you're trying to discover an exoplanet using the Doppler methodology, you need bright host stars. So you need stars that are really bright, either nearby or giant planets, but giants are hard anyways. Then you need basically to monitor these in color shifts for long times, and then you can actually find them. However, the number you will eventually find is fairly limited. However, for the second method that I will now define using this animation, you basically have a background star like the one that is illustrated here, and then you have an opaque object that's actually an exoplanet that is transiting, so-called, the star. Because of this transit, the total amount of light that you receive from the background star decreases, and this happens for a particular amount, duration of time, and it also happens at particular intervals of time. So this is a periodic event with a particular shape in the amount of light that we receive as a function of time. And from this shape and the so-called depth of the signal, we can actually infer many characteristics. The most important such characteristic is actually the size, or in fact the relative size of the planet and the star. But we usually know the size of the star through other means, like measuring, for example, the distance to it. And since we can calculate its temperature as well, we can actually kind of infer its radius. So using that information, we can then infer also the planetary radius, which is a highly convolved pipeline, but it actually works. And we now know the radius of many thousands of exoplanets, more than 3,000 of them. And this is indeed remarkable because now, by now, we can actually even study the features in the so-called radius distribution of such planets and try to link these to the very formation of exoplanets. So when I mention transit methods, I think you will definitely remember Kepler telescope, because that was historically the first large-scale survey of the sky for transiting exoplanets, and it actually discovered almost 3,000 of them. But actually, there's a new mission called TESS, which, well, I guess when I say new, it's relatively new. It's been in space for about for longer than 2 years by now, and it will continue, hopefully, to function as planned for many more years. And it's been also finding more transiting exoplanets, but from a different population of exoplanets that I will define more clearly very soon. But just to put this into context, I would like to highlight one phenomena that happens in our solar system that you may have realized or may potentially have missed, which is that our inner planet, Mercury, actually transits the sun. And this happens about 10 times per century. Here, let me highlight Mercury in a photograph of the sun. That's Mercury with its shadow on the sun. And using this, for example, you can very precisely measure the radius of Mercury. You can also do this for Venus, but Venus transits much more seldomly. So it's very rare, in fact. It happened very early 2000s twice, and the next time it will happen is sometime in the 20, I believe, second century. So more time. We probably, our generation, will not see that. Anyway, so that's a very rare event, but and that's mostly because the synodic period of Venus and our own Earth is very large. So after this highlight, one more thing. So here, just another photograph of Mercury, and I just want to highlight that in our investigation of light curves, there are also so-called background systematics. Some of these are directly coming from how the telescope is functioning, but also astrophysical backgrounds. Our major astrophysical background is actually just stars that eclipse each other. So not a planet plus a star, but rather two stars that eclipse each other. And as a result, you tend to get the same type of modulation that I was showing. But another type of background for us is stellar spots. And stellar spots, especially stellar variability of even different kinds, in general can mimic sometimes transit signals. So we have to be careful about those. Not stellar spots per se, but other kinds of stellar variability can also mimic transit signals. And stellar spots can also definitely contaminate Doppler measurements in the other detection method that I briefly described in the very early stages of this talk. So I've talked about the legacy of Kepler kind of verbally, and here is an image of or a plot of the radius and period distribution, or orbital period distribution, of known exoplanets from this summer. So obviously this plot is continually getting updated, so there may be planets that are missing here, but and in fact these are only the confirmed ones, but there are many exoplanetary systems that have not yet been confirmed, but have a really large probability of eventually getting validated. So, and these are in the works. So this plot is a highly dynamic one. Let me point that out. And here you're saying basically that the plot is dominated by green color, which is essentially saying that the number of transiting planets is really dominant, although it also has to do probably with the order with which markers are plotted. But indeed, the transiting planets indeed are dominant if you look at the overall population of exoplanets. And then with about 800 to 900 exoplanets, radial velocity detections then are the second one. And then there are many minor ones that I will not have time to discuss today. But there are several features that I can point to in this particular figure. One is that the existence of hot Jupiters, which is the population basically larger than 10 Earth radius roughly, and just with an orbital period less than about 10 days. Those are called hot Jupiters to the upper left. And then on the lower side, we have the so-called small planets. We usually like to call small planets those that have radii less than 4 Earth radii. And those planets, which in fact we know many of them, there are subpopulations of those. Whenever they're below 2 Earth radii, we call them so-called super Earths, or between 1.25 roughly and 2. We call them super Earths. There are those that are very similar to Earth as well, especially in terms of radius, but not in terms of orbital period, unfortunately. That is, just let me highlight, we do not yet have an analog of Earth around a sun-like star with an Earth-like radius and an Earth-like orbital period. That simply does not exist yet. We do not yet have the photometric precision as well as the temporal baseline, follow-up baseline, to actually find and be sensitive to such exoplanets, unfortunately. But that time will eventually come. And as we integrate more photons over a longer baseline with good precision, eventually our surveys will find exoplanets that are as small as Earth and with orbital periods in excess of 100 days. And then they will have really good chances of being in the habitable zone. Okay, so for some time it's been discussed that whether there was the potential of defining an analog of Moore's law in exoplanet science, that whether the number of exoplanets discovered will be increasing logarithmically. We do not yet know if this is going to continue. However, we do know that in the next few years this may be stalled for good reasons, because TESS is not really designed to find and be like a statistical survey just like Kepler. However, TESS is really doing important job in finding exoplanets that are amenable to mass characterization as well as atmospheric characterization. So it is essentially finding that exoplanet population which is going to allow us to do detailed studies. However, there will be many exoplanets, many thousands and tens of thousands of them, which are not going to be amenable to mass measurements, and hence we will not know whether, for example, their atmospheric compositions are, bulk compositions are. We will not be able to break many degeneracies in their characteristics, but they will still exist as statistics. And there will be hopefully future missions that will allow us to do this using lensing surveys. So this Moore's-like law might eventually continue maybe towards the end of the decade or middle of the decade, this 2020 decade. Okay, so this is just another way of showing the same thing, which I will just skip. One thing that you may wonder is, why go to space? So there are many, ground-based telescopes, and one thing you may wonder is, like, what's so special about space photometry for exoplanet science? Well, the thing is, for transiting exoplanets, you're trying to find relative fluxes. You're essentially measuring the light that comes from the star, and you're trying to find features, dips, etc., in them. And in order to do so, you need a good photometric precision. And unfortunately, our atmosphere has a phenomenon called scintillation. That scintillation is pretty much due to hot air rising, creating turbulence. And that unfortunately results in excess photometric uncertainty or jitter that we cannot decrease. So as a result, if you want to study, for example, small planets, whose radius ratio will turn into a really small transit depth, then you actually have to go to space. And that's why Kepler and TESS and telescopes alike actually exist. Okay, so a couple of pretty pictures, hopefully, for TESS that will increase your interest in this just through visuals. So this is TESS. And you see that now it has 4 cameras, so camera 1 through 4, and each camera observes simultaneously for about a month. Well, in in pairs of 2-week periods. Basically, that's in total, that's what we call a sector. And then there are basically 13 sectors in a given year, and the nominal mission was actually 2 years. In one sector, we measured we scanned the southern sky, and then in the second year, we scanned the northern sky, or most of it. There was some change to the observation strategy, but a minor one. And then now we're in the extended mission, so redoing the sky, and then there will be a couple of new observations of the ecliptic plane, which will be novel, and we will reobserve many targets from the K2 mission then. However, you can basically think of TESS as a full sky mission, essentially trying to find exoplanets across the full sky. And while doing so, it is obviously finding those that are really amenable to further characterization. So the focus is really different from that of Kepler. And TESS is a bit redward as well. So its passband is really tuned to M dwarfs, those stars that are really that have really red colors. So you're seeing JWST in this animation, which is obviously unrelated to TESS, but because this is an exoplanet talk, I just need to also mention that once transit surveys are done with their task and give you a list of planets amenable to atmospheric characterization, the next question you ask is, for those transiting exoplanets, can I actually study their atmosphere? There are two ways of doing this. There's emission spectroscopy and transmission spectroscopy, if you want to do spectroscopy. There's also a couple of things you can do with the white light, so broadband light. You can basically study their phase curve, which will tell you about the heat recirculation on the planet, their albedo, etc. But if you want to actually study the composition, then you need lines, and for that you need spectroscopy. So there are two ways of doing this, either transmission or emission. And emission is only applicable to those that are actually hot. So you might know that planets have no internal energy source other than those that is remnant from the formation, or there are other secondary things like their tidal dissipation, sometimes magnetic effects, etc., that can actually generate some internal energy. But leaving them aside, basically there's no internal energy source. So you basically either want hot planets or young planets, which tend to be hot anyways. So that's very restricted. However, the transmission spectroscopy is very generic. So whenever you have a transiting exoplanet and a somewhat puffy atmosphere, you can actually study the absorption spectrum of the molecules and species in its atmosphere, which is really cool. So this is TRAPPIST-1. I'm sure you've heard about it. It just it somehow manages to get on the news kind of periodically. Although with JWST, I think we will hear more about it very soon. I mean, once JWST observes these planets, because there's 7 transiting planets and they're very accessible to atmospheric characterization. And JWST will be attempting to do that. And these are all small planets, very similar to the Earth. Okay, so with that, I would like to just switch the focus a bit. So this was a fairly generic introduction to exoplanet science. I would like to just highlight one specific example of a planetary system that have been discovered very recently. And then I will just not keep it long and get any questions you may have. So hopefully the rest will be fairly quick, and then we'll get to the questions. So in TESS, whenever we have a target that transits periodically and we conclude that the transits are of planetary nature, then we call it a so-called TOI, TESS Object of Interest. And there are many of them, currently about 2,400 of those. And some of these obviously turn out to be false positives. Not all exoplanets that pass the initial triage actually turn out to be planets. And some are very hard to follow up. So even though we do not rule them out, some will essentially just linger as TOIs for many years probably, but some eventually turn out to be validated or confirmed, and then we can start doing further science with these. So I will highlight the TOI 1233 system. So this is catalog number HD Henry Draper's catalog 108-236. What's so special about this system is that there are actually 4 small planets around it, and all transiting, and discovered by TESS 2 years ago. And as a disclaimer, I led the study of the discovery of and eventual validation of this system. And here you're seeing the TESS light curve from sector 10 and 11 of the southern observations. So each planet's transit is colored a bit differently here with a different color. So you see that B, C, D, and E, which are letters given to different planets, B being the innermost one, E being the outermost one. So you can also tell that their temperatures will scale accordingly. And here you see the phase curve. So phase curve is essentially a data product that you get once you predict or infer that there's a periodic event in a time series, and then you take that period and phase fold onto that period, and then you get so-called phase curves. So then you can study the transit features, the transit shape, etc., using this phase curve. So these are the phase curves of B, C, and D planets. And then once, obviously, we get this initial sign through some data analysis, we have to then make sure that, for example, that the star does not have a neighbor, because if it does, then it introduces so-called dilution into the calculation, which would make the transiting planets actually larger. So we have to make sure that that's not the case. And then we figured that the planet, the star is actually single, up to obviously some limitations, but we were able to put upper constraints on the mass of any neighboring star. And then there was a radial velocity follow-up. So in the very beginning of the talk, I mentioned the Doppler methodology of finding transiting planets. So you can also use that methodology to follow up transiting exoplanets, which is very favorable, because when a planet is transiting, it has an inclination of 90 degrees. So it's actually optimizing the amplitude of the Doppler signal that you'd get from a system. And it also breaks the degeneracy between the inclination and I mean, eventually when we measure, we only know the projected velocity of the planet, so that breaks that degeneracy against the inclination. So basically, by first doing rough, not so precise radial velocity follow-up, and then continuing that with precise radial velocity follow-up, we concluded that the star is single and that the orbiting objects are substellar. There was also some photometric seeing limited follow-up of the system, and this is basically to make sure that not even one of the transiting signals that we get is coming from a background star. So you still need to make sure that's the case, because test pixels are huge, and there's usually a confusion that comes from that. So one thing to highlight about HD 108-236 is that this system is the brightest sun-like star on the sky to host at least 4 transiting exoplanets. Although we know many thousands of exoplanets by now, many transit. Well, first of all, about 3,000 of those actually transit, and many of those actually transit faint stars. There are those that transit bright and even much brighter stars than 108 through 36. But then not many of those are multiplanetary, and not any of those actually have at least 4 transiting planets. Now you would ask, so what's so special about having a bright star with many transiting planets? Well, this is ideal for atmospheric characterization, because if you have a bright star, first of all, it increases your signal to noise in terms of mass measurements and any subsequent atmospheric characterization that you attempt to do. And then, because it's a multiplanetary systems with small planets, it actually allows you to do comparative atmospheric characterization. So when we try to characterize atmospheres, there are problems that arise, because when you go from one star to the other, the whole insolation history is different, the stellar age is different, stellar type is different, and it's really hard to tie it back to and interpret these results that come from independent systems on a common basis. However, when you have a system with multiple planets that have shared common insolation history, obviously the level of insolation will be different, but the spectrum of light that they get and the time series of amplitude will essentially be similar. Then you can actually have a controlled experiment over many of these and focus on the composition and the evolution of the atmosphere directly. And that's so exciting about this system. So you see here that the temperature, the equilibrium temperature, and the radius of the exoplanets in this system particularly span a large range. And this plane of radius versus temperature is really like the fundamental plane of the atmospheric characterization, because as you move on this plane, you get really different chemistry on the system, on the exoplanet, and you really want to sample different points in the system in order to really get a big picture of how atmospheres work on exoplanets. So I think in the very beginning of the talk, I alluded to a feature on the histogram of radius distribution. I think I may not even have mentioned it, but I did say that we studied the distribution of radii, and this feature is called the radius valley. It's been known since about 3 years by now. And with black, you're basically seeing that for the known special subset of exoplanets whose radii are precisely known. And then overplotted is the 4 transiting exoplanets from this system. And you can clearly see that it spans a large range of this. And there's one that actually is almost in the center of this valley at about 1.6 Earth radii. And this is important because we believe that it's a transitional regime. So these systems that are in the valley or close to it probably have dynamic atmospheres, or at least partially outgassed and partially primordial atmospheres. So they're rich in terms of information content, and we would like to understand them as much as possible. And just to point out for this system that the innermost planet is likely a super Earth with terrestrial composition with an outgassed atmosphere potentially, and the other 3 are sub-Neptunes. This is essentially coming from radius mass relations that we have on the known planet population. However, the mass measurement of these systems is well underway and will be public very soon. And yeah, so just to sum up, this is a so-called tightly coupled or close-in system and compact system. So when you have a compact system, you kind of ask yourself the question, can I actually fill in the orbital or dynamic gaps, which obviously you can attempt to do so. So here in this system, there's a dynamic gap between C and D. So we were wondering whether we can actually fit a transiting or non-transiting exoplanet in that regime, and that is well within the potential. I mean, that is possible. However, we do not yet have evidence for it. However, TESS is going to reobserve the system, and more follow-up is underway. So hopefully, we may eventually discover more planets in the system, either within the orbital gap or outside as outer companions. And there's obviously a single transiting candidate in the system as well. With such a rich system, you kind of expect that there would be even more transiting exoplanets. We just do not yet have the data to investigate that in great detail. However, as I said, TESS is going to reobserve this system, and it's also been observed by other telescopes. So hopefully you will hear more about this system in the future. Okay, so with that, I'm going to kind of conclude here. Let me kind of sum it up. We have this big exoplanet research program that's been up for at least 30 years and will continue to flourish even further into the future. The focus of exoplanet science may change a bit from really individual detection to population models, and extending those population models not to just things like as simple as radius, mass, etc., but to bulk composition and atmospheric composition, and hopefully constrained models of planetary formation and evolution, and eventually tie these all back to our Earth and the solar system. We would like to answer questions like whether our solar system is unique in any way, because there is a prior degree of belief to say that our system must be unique in some sense because it has produced life. So we kind of ask ourselves this question with the expectation that it's going to tell us something useful about how life started. So basically, we would like to understand answers to these questions and propose new questions along the way. And Exoplanet program is really proceeding in a robust manner to answer such questions and make new discoveries, especially with the new generation of telescopes that will be coming online, with the most important one being JWST. With that, I'll conclude and take any questions. Thank you very much.
Thank you for your nice presentation. So if you allow, we can start our discussion session. So we got two questions in the inbox. So the first is, what is the transit of Mercury planet? Maybe you have already.
Sorry, what is transit? Oh, transit of Mercury. Yeah, so, well, Mercury is an inner planet. So because it's an inner planet and it doesn't have an orbital inclination that would preclude its transits, we can actually see the transit pass in front of the sun periodically, about 10 times or 13 times per century. And that allows us to constrain many properties of the inner solar system, the most important being the orbital period of Mercury, as well as the radius of Mercury. It basically is one of the historically it's one of the precision measurements in astronomy, and currently it's not as important as it used to be in the past, but it's still for amateurs and for follow-up reasons, it's an important observable.
Thank you. There is another question. So can dark matter interact with planet? And if interact,
dark matter probably, it interacts in the sense that it gravitates. Dark matter is massive, planets are massive, so they will definitely interact, and they may have some observable departure from a universe where dark matter did not exist. The only problem is that dark matter is a cosmological problem. So it shows up mostly at really large scales and especially at galactic scales. So trying to search for the signature of dark matter in exoplanets has the problem that the signal will be very weak. You have to kind of find special circumstances in which they make a difference. You can, look for external heating to exoplanets. You can look for, dynamic departures. Since you know the masses in a given system. Although with the solar system, for example, we don't even yet know whether there's the ninth planet or not. So there are many questions that are not answered. So I don't think there will be a data set soon that will allow us to study dark matter using exoplanets directly or dynamically. But using energetics, it may be possible at some point.
Okay, thank you. This may be the last question. So, is it possible to find life in other planet in the universe? Distance of light.
Find life on other planets? Yeah, so
Yeah,
that is
life. Yeah,
that is
is it
certainly
possible to
possible.
find life
We
in the
just
planet?
do not know where and when. Currently, the searches are focused towards two channels, either technosignatures or biosignatures. However, I would say that our understanding of technosignatures is and also of biosignatures, so to speak, are really primitive because the problem is that we do not yet have a full understanding of the astrophysical foregrounds and backgrounds, like what is basically your null hypothesis when you're looking at a data set, and what is it that you are going to define as technosignature or biosignnature. That is really not very well defined at this point. Biosignatures, there are some candidates. However, ruling out all the astrophysical processes that can potentially produce a biosignature is really hard. And similarly for technosignatures, like when we first discovered, for example, pulsars, you could treat that as a technosignature because it's a periodic signal in radio waves, but it eventually turned out to be pulsars, which are just astrophysical objects, compact objects. So again, defining that is really hard, although if eventually we see something, we will know that it looks very weird and try to investigate further.
Thank you for your nice presentation and wonderful discussion sessions. So we have organized this program to motivate and encourage our students in this corona pandemic situation, and we have successfully completed our 96, and today it's 97, and we are going to celebrate our 100th International Physics webinar on December 4th with Nobel laureate of 2012. So I think all the viewers and all the students are invited to our 100th episode, and you also are invited. So if you are interested, you can join with us. So thanks again, Dr. Dyson, so for accepting our invitation. So it's our pleasure actually to host you in our International Physics webinar. And I think students have learned a lot of things about exoplanets and other things, and they might be fall in love in astrophysics in their research in future. So thanks again, and hopefully, if you have time, we can arrange another webinar with you in future. So bye for today, and good night.
Thank you very much for listening, and have a nice day.